Okay. Hi. So today, tutorial 8, we're going to talk about really interesting and pretty new topic called geometric deep learning. Basically, deep learning on non-Euclidean domains. So we'll cover the basic theory that's needed. So it's quite a few things about filtering in general, and then how to filter on graphs, and the Laplacians of graphs and their meanings, how to define convolutional layers in the both frequency and in the spatial domain, but over graphs. And we'll see a demo application of how to classify nodes in a graph using a semi-supervised approach. Okay, let's go. So first, let's remind ourselves about the theory regarding non-Euclidean domains. So we'll build up from our convolutional layers that we used heavily. Okay, so in most of our models so far, we use these convolutional layers, which were defined like these. If you remember, they operate on tensors containing multiple feature maps, and they produce output feature maps, which are convolutions between different filters and different feature maps. So every output feature map is a function of all the input feature maps. Okay, since we have these multiple filters, when we actually talked about implementing it, we imagined we have these 3D filters, but this is another way to write it using specifically a convolution. Okay, and if you remember, we liked these layers because they had some important advantages for us. So I'll briefly remind you that the main advantages were the fact that the number of parameters did not depend on the input dimensions, and that you can share parameters across space. So this was actually both efficient in terms of memory and actually useful in terms of images, since in images there are features that you can define that are relevant throughout the image. Okay, so these were the main advantages of convolutional layers. Okay, so to kind of apply this idea to other domains that are not images or non-Euclidean domains, we need to kind of better define what convolutions are and find another way to define them. So if you probably you've seen the actual definition of what a convolution is. It's basically for each output element you have to compute this the sum of two functions. So for example, if this is our filter, then we take our flipped filter and sum it with our actual input signal, which is x. So this is a visualization. You can really imagine how you're sliding a flipped filter over your data. So at each point in the output, you have to slide the shifted filter over the whole input. So this is a visualization. And it turns out that actually this is a linear operation. So like any linear operation, you can use a matrix to define the operation. And in the case of convolutions, which are shift equivalent, which means that if you take a shifted input, you'll get a shifted output by the same amount. You can represent these operations using Toeplitz matrices. So a really important feature of Toeplitz matrices is that you can compute an eigen-decomposition of them, and you have the same eigenvectors for any Toeplitz matrix. And these eigenvectors are actually these eigenvectors, which are the Fourier basis. So here we defined it with a discrete spatial index and a continuous frequency index. So these are just complex exponentials defined over some multi-index and in a continuous frequency. Okay, so these are discrete harmonics, and it turns out that all the Toeplitz operators have these eigenvectors, and it's really easy to see why. Because if you just take a Toeplitz operator and say that you want to represent it as a convolution and just plug it in to the regular definition of a convolution, then what you get is your same vector, and here you get an inner product over the space of square summable sequences. And this inner product is a scalar, which is your eigenvalue. Okay, so it's really easy to see that this is an eigen basis for all the top-place operators. Okay, so we just define it like that, as this inner product. And since this is the Fourier basis, or then we can say that this is actually when you project some sequence x using these vectors, then we call it a Fourier transform. Okay, so you have the regular Fourier transform, and which is defined by this inner product on this domain, and you have the inverse, which is the corresponding inner product, but on the continuous domain of square integrable functions. So you have the Fourier transform and its inverse, and you can define it like that. Okay, and the crucial thing that we need for the next part is that if you that using the previous result, that you can write any time domain convolution in terms of its frequency domain product. So just by using the definition that we saw, if you take a convolution and write it like that with a topless matrix, and then you just take x and write it in terms of its coordinates. So this is the projected coordinate on the eigenvector. So this is the coefficient for this basis vector. And since then you can move the matrix inside, and since you have this is an eigenvector, you just get the eigenvalue back. Okay, times the same vector. So what you got here is an inner product in the frequency domain of the Fourier coefficients of your input and the filter. Okay, which you can write like that. So this is the convolution theorem. Just we wrote it in a more compact way. Okay, so now that we have that in mind, then we can extend the whole notion to graphs. Okay, so we'll discuss graphs because they're really general, and you can use them to represent various kinds of non-Euclidean domains. And briefly, just how to define them. Then probably you've seen a lot of graphs by now, but we define them using vertices. So we have just a set of n vertices and a set of edges, which are pairs of vertices. And generally, you can give each vertex a weight, and you can give each edge a weight. So generally, you have this weight matrix, which is the diagonal matrix of edge weights, vertex weights, sorry. And you have this edge weight matrix, which is also the adjacency matrix. So it would be 0 if there is no edge connecting to vertices, and otherwise it would be some weight. Okay, so you can define a signal on a graph by just giving every node in the graph some value. The value can be a scalar or a vector. So you can just say for each vertex I have a value of my signal, and you can represent signals as just vectors in Rn. If you have n nodes, then you have these vectors, these n length vectors representing different signals. So this is a space, okay, and you can define, for example, inner products on the space. If you have vertex weights, then you have to include these weights in the product. But usually we'll normalize our graphs, so we don't really have vertex weights. Okay, and similarly, you can define a signal on edges. It's really the same idea. You just give every edge a value. So this time it would be a matrix, and you can also, it's a space where you can define an inner product, and everything is nice and well defined. Okay, so the important thing to use in our context would be this graph Laplacian, which is it's kind of a measure of smoothness. It's really connected to the idea of a second derivative, which kind of measures the smoothness of a function. So you'll see that it really connects to smoothness in of the rate of change of your signal on the vertices, for example. So how quickly does it change between adjacent vertices? The way it's defined, I think we saw in the lecture that it was defined using a gradient and a graph divergence. So this was the result, and what you can see is it's kind of a weighted difference between the value of a specific node and the values of nodes around it. That's what you see here. So it's the sum of weights of a specific node, touching a specific node. This is weighting the node's value, and you subtract the weighted values of the adjacent nodes. So these are the adjacent nodes. Okay. So now that we have that, then we can represent it as a matrix. So again, generally, if you have vertex weights, then you have this factor here. But usually, if you normalize your graph, then the regular Laplacian definition is just this adjacency, this degree matrix D minus the adjacency matrix. Or, as you saw, there were other ways to normalize, which we'll see an example of when we see our application later. We'll see a different kind of normalized Laplacian. Okay, and this degree matrix is simply the sum of weights touching every edge. So this is, for example, the element in the ith diagonal of the degree matrix. Okay, so this is the graph Laplacian. And interestingly, the Laplacian always has an eigen-decomposition, and the eigen-decomposition of the graph Laplacian has very important features. So if we return, just for a second, to the Euclidean domain, it turns out that since the Laplacian is also a translation equivalent operator, it also has a Fourier eigenbasis, and you can, for example, see here that the Laplacian of this harmonic function is just some eigen value times the function. And similarly, for graphs, we can compute these eigenvectors of the graph Laplacian matrix, and we can actually use them to represent functions over the graph using the basis of the eigen-decomposition of the Laplacian. Okay, so this is just a regular eigen-decomposition. You can see we have a matrix here of our eigenvectors in its columns. So again, if we have n nodes in our graph, we'll have an n by n matrix here containing the eigenvectors of the Laplacian, and this matrix is the eigenvalues as a diagonal matrix. Okay, so we have the eigen-decomposition. And if we have vertex weights, then we don't really have an orthonormal decomposition. We have an a-orthonormal, which means we have this a here. But again, we can normalize it and get a regular orthonormal decomposition. Okay, so interestingly, it can be shown that when you take a graph Laplacian and compute this eigen-decomposition, you get a basis that's composed of the smoothest functions that you can in terms of some kind of energy metric. So you get very, very smooth functions, and as you increase if you order them by the magnitude of the eigenvalue, then they become less and less smooth, or higher, or represent some higher frequencies. So usually, you can see always the first eigenfunction will be some constant, and then you can see smooth functions, and they become less smooth, higher frequencies as you go up. So you can see, for example, here in the Euclidean domain, this is just the Fourier basis, and on some kind of manifold you can see the smoothness, and on some kind of graph you can see again smoothness, and then more high frequencies emerging. Okay. So what we did is we said that these Laplacian eigenvectors are a space of the functions over the graph nodes. So we can represent any function over the graph as a linear combination of these eigenvectors of Laplacian. So we just need the coordinate. So again, all we do, since we have defined an inner product in this space, we just project our vector. So f here is a vector which gives some value to each node. So we just project it onto the kth, for example, the kth eigen vector, and we get the coordinate in that representation, and then we just sum them. So we can represent f in this way. And then we can just define that this is also the Fourier basis. Since in the Euclidean domain, the eigen decomposition of the Laplacian is the Fourier basis, we can just say that it's the same here. And we define the Fourier transforms of functions on the graph similarly. So all we have to do is just use these eigenvectors of the Laplacian. The difference is that we get different vectors for each graph. Okay, so it's not a single basis like in the Euclidean domain. Okay, so now that we have that, now we can define the first type of convolution layer for graphs. So this is the spectral convolution layer. We'll see another type after that. So again, if you remember the convolution theorem that we started from, we can apply in the Euclidean case. We can either do a convolution, which is also represented as a topless matrix, and we can say that it's equivalent to taking a product in the Fourier space and then using the reverse Fourier transform. Okay, so we got this directly just by definition when we plugged the harmonics into this definition of convolution. So what we can do in the non-Euclidean domain, since we can't really define the convolution itself because we can't shift anything around, we can't use the shifted version of any filter. It's not defined how to shift something on a graph. So all we have to do is we just skip this part. We say that our filter on our operation on f is just defined as this part. Okay, so we just say we define it as the inverse Fourier transform of the Fourier coefficients multiplied by the filter coefficients. Okay, so we just skip the part that's not defined and say that, okay, now we have a new definition for how to define an operation on a graph. So if we do that, then just using the definitions, we need our Fourier transform of our function. Okay, so these are the Fourier coefficients, and this is the Fourier coefficients of our filter. We get them using a projection using the eigenvectors. So what you can see here is just, this is the forward Fourier transform, and then we weight the result using a filter, and then we do the reverse transform. Okay, so it can be also written like this in matrix notation. So we're taking our vertex field, which is assigning a value for each vertex, and just multiplying by this matrix, which does the forward Fourier transform, then does weighting. This is a diagonal matrix, and then does the inverse Fourier transform. Okay, so now we found a way to define our convolution on the graph. All we have to do is compute these eigenvalues and eigenvectors. Okay, so after we have that, we can define a spectral convolutional layer, which is defined like that. So if you look at this, you can see that we're taking our feature maps. So now our feature maps are a single value of a feature for every node, and we're using this as our transformation. And the learned parameters are the elements on this diagonal matrix W. Okay. Great, but the problem is that this way of defining a convolution layer on graphs, the spectral way, is kind of limited. And if anyone remembers why, now it would be a good time to remind me. And remember, just by looking at this, you can see maybe some limitations of this method. Why is it bad? Lots of computations. Okay, yeah, that's one problem. So these matrices are generally non-sparse. Okay, just full n by n matrices. There's no FFT. There's no fast way to compute the Fourier transform. We really have to do this matrix multiply. So that's one problem. The other problem is that we have n. This is an n by n diagonal matrix, so we have n learnable parameters, where n is the number of graph nodes. So that's another issue, since now it's not really like a convolutional layer where our number of parameters does not depend on the input size. So now the graph size defines the number of parameters. So it's a problem. And moreover, we have a degree of freedom for each of these eigenvectors. And remember that the eigenvectors, as you go up in as you go up in their order, going to higher eigenvalues, then they represent higher frequencies. So you potentially can insert some really high frequencies, which will make your filter non-smooth in frequency. Which, if you recall, it relates to non-localized in space. So again, it's not exactly what we want when we define convolution layers. So the fact that you actually have a complete degree of freedom for each eigenvector will allow you to really insert some high frequencies into your filter and make it non-smooth. Okay, and you have to compute both directions. So generally, this is very, very slow since it's n squared, and it again depends on the size of the graph. Okay, and like I said, since we're learning these filters, but we have these eigenvectors on each side, then they really depend on the specific graph Laplacian decomposition. So it won't generalize well to another graph, even if it's a similar graph. So here's an example from a manifold, but it's really the same idea. If we have this manifold and we have a signal, so here we have a signal on the manifold, and then we apply some filter using this spectral method. So this is an edge detection filter, as you can see it. This is our result. It kind of detects the edges of these features. But if you take a manifold that's similar, this is an isometry of the manifold, so it's not deformed, it's just shifted, and you use the same filter coefficients but with a different eigen decomposition, then you get a different result. It doesn't have the same meaning anymore. So that's kind of limiting. If you want to generalize to different graphs, even if they're similar, we might not be able to. So based on that, we define a different way to do it, called the spatial convolutional layer for graphs. So this is the second way. And the idea is to try to overcome these drawbacks, but we still need to understand where it's coming from. Okay. So first, we'll use interpolations of the Laplacian eigenvalues instead, and this will address the first two drawbacks, which we saw. So let's start with the first change we'll do is we'll define our learned features as a diagonal matrix defined by this term. So we use a constant matrix B, which is some function, some family of functions, which are these betas applied to the eigenvalues of the Laplacian, and we only have q parameters. We set some number q, which is the same number as our different functions, and we say that the filter parameters that we learn are based on this multiplication, which means that we only have actually q parameters for each of the filters. Okay, and these betas are smooth functions. So we'll see what they do in a second. The first advantage now is that the number of parameters does not depend on the domain size, and we're using interpolation. We're interpolating over these eigenvectors to get our filter parameters. So we get something smoother. We don't have the same number of degrees of freedom. We can't really insert these very high frequencies as easily as before. So the number of parameters in our layer now will actually only be, well, we saw we have q for each filter, but how many filters we have, it depends on the number of input and output feature maps. Okay, so we have for m input and m prime output feature maps, so this is the number of parameters. We do not depend on n anymore. And one choice that's popular is to select the beta function as polynomials, and then if you write remember it was defined as beta times alpha, and then a diagonal matrix of that. So in each diagonal element here we have this sum. Okay. So if you just use polynomial functions where beta k is just lambda to the kth power, then you can write it like that, and it's actually you can easily see that you can take out the sum and you get powers of the eigenvalue matrix. Okay, and since this is an eigen-decomposition, it also means that these are actually powers of the Laplacian matrix. So that's one way to kind of throw away the Fourier transform, but get something that has a similar meaning. And then we have this spatial version, and the spatial version, at least for those specific functions of beta that we saw, is defined like that. So you take your input feature maps and use powers of the Laplacian weighted by these q weights for each input-output pair. Okay, so this is now the spatial definition, and it has some advantages. First of all, it's spatial. We don't have this inverse and forward Fourier transform. We don't have to compute the Laplacian decomposition. There is some meaning to this kth power of the Laplacian, because it's a local operation. Since the Laplacian is doing a weighted difference between a specific node and its neighbors, the kth power is actually just looking at larger and larger k rings around the nodes. Now you still have an n by n matrix here to multiply, but arguably, as opposed to the eigenvectors matrix that we had before, the Laplacian might be sparse. It depends on the graph. It might be a very sparse matrix, so you might get some benefit computationally from that. Okay, so this is our spatial version. Yeah. No, I don't think it's the same. Since you're using the same, you have the same features. You have the same feature maps all the time. You're just applying more and more and summing them. So it's like you're combining features from adjacent nodes around your node, combining them, creating a new feature map, and then taking that and multiplying it again. So it's kind of, it keeps summing like outer in an outward direction from each node. So you get like these rings. Okay, but it might be less sparse. I mean, the more powers you take, you get a less sparse matrix, and then you won't be able to maybe benefit from the sparsity. And there are many papers that define different functions that actually are used. So instead of just polynomials, they define other types of polynomials, like there's Chebyshev polynomials and Cayley polynomials, and there's various famous papers that just do different functions here of the Laplacian. Okay, and you can just write it like that more generally, where you have some function of the Laplacian, you sum these functions times this is now a matrix of the features, so this is our feature maps. Okay, so it would be an n nodes by m features matrix, and this part here would combine your features, and this part here would use these feature combinations to generate your output feature maps. Okay, so again, there are various functions that can be used, and they have different properties, and this is a very useful way to define filters on graphs. Okay, so now let's look at an example application using a similar approach to that. Okay. So our application will be semi-supervised node classification. We have to classify nodes in a small social network graph, and we only have true labels for a small subset of the nodes. Okay, so we have the graph. The graph is given. So there are some problems where you don't really have the graph, and you have to construct it from the data. But in our case, we know the graph, and we know the meaning of the graph, but we need to classify each node, but we don't have the labels for all the nodes. We just have a very tiny subset of labels. Okay, so we'll implement an approach based on this paper. You can see the linked paper if you want. Okay, so the dataset that we'll use is a really toy small graph called the Zachary's Karate Club. It's from an old anthropology paper, and they actually, in one of the appendices of this paper, they show this example, similar example. So it's a really nice data set because it's really small, but it has this social connectivity with two communities in the graph. So basically, it's based on members of some karate club, and the links. So each node in the graph is a member of this club, and the links between nodes, or the edges of the graph, represent the fact that two people interacted outside the club. So they know each other from outside the club. So at one point, the club split into two groups, okay, because there was a conflict between the instructor and the administrator of the club, and the club split into two. And our goal will be to predict which member after the club split decided to join which of these people. So the club split into two around the instructor and the administrator, and we have to kind of guess where each member went according to the connectivity that represents their interaction outside the club. Okay, so that's the idea in this data set. So we're using this nice library called Network X. It's a useful graph library. Has lots of stuff. Importantly, one of the things it has included is a bunch of toy graphs and lots of functions to generate graphs. So it actually has this data set included, so it's really nice. We don't have to do anything. We just call the function, and we get this graph. And first of all, let's visualize it. So I'm using, again, the same library just to, one more thing. I just I just know from the definition of the dataset that the instructor has the node ID 0 and the admin has node ID 33. The number of the nodes in the graph is just 34. Okay, so I know these two nodes, and these are the nodes that I will have labels for. Okay, so let's just look at the graph for a second. I'm just plotting it. Okay, I hope you can see. So this is our graph. This is the instructor node, and this is the administrator node. And these are other members in this community. And again, the edges represent some kind of interaction between the members. So this is what we're working with. You can see that lots of people are connected to each of these, but there are various other connections going on. It's kind of hard to see just by looking at it that it's very clear. I mean, community, especially in the middle here, stuff like that. Maybe it's obvious that some nodes should belong to this group, to the instructor group, but it's not completely obvious for all the nodes. Okay, just by looking at it. Okay, so just because we're working with a graph and we spoke about the spectrum and Fourier basis, let's apply what we learned. Okay, so the first thing that we'll do is compute the adjacency matrix. I'm sorry, it's a little confusing. I'm calling the adjacency matrix here A. It was W before, but now from now it will be A. Okay, A. We don't have vertex weights, so A is our adjacency matrix. So I'm just using the definition of the Laplacian. I'm taking my adjacency matrix, calculating a degree matrix, and defining the Laplacian as the difference between the degree and the adjacency, and then computing a linear eigen-decomposition of this matrix. So I'm getting the eigenvalues and the eigenvectors. So this is the spectrum. This is what's known as the spectrum of the graph. It's the magnitude of the eigen values. And more interestingly, if we plot the graph again, but color the nodes. So what I'm doing here is I'm using this draw function to plot the graph. And each time I'm putting the same nodes in the same locations, but I'm giving them a color according to I'm using the ith eigenvector here. So each of these graphs is using a different eigenvector for color. So we can see really that the first one has a constant color, and this one looks kind of smooth. Okay, it's kind of a smooth transition, and it gets arguably more high frequency. It's kind of hard to see with such a small graph, and it's very irregular. But really, it's the idea that we saw before. You can really visualize it. Okay. So let's look at our data in terms of our features and our targets. So what we have is that each node in the graph has this extra attribute, which represents the member's post-split affiliation. So this is the actual ground truth label for each of the graph nodes, and we'll use it at test time, but in training time we'll only use the instructor and the administrator label. So obviously the instructor belongs to the instructor class, and the administrator belongs to the administrator class. So that's their post-split affiliation. Okay, and to really demonstrate that the graph structure is helping us understand the correct labeling of each node, we're not really giving any features to the node. So we'll use just an identity matrix, or we'll use a one-hot encoding. So each node will have a one-hot vector, where one is the node ID as its feature vector. So it's not really giving any information besides the ID of the node, okay? Because we want to take these non-informative features, combine them using the graph structure, and then get some prediction for each node. Okay, so now let's construct that. So X's are feature maps. We'll just create an identity matrix, okay? And to create our labels, you can see that our nodes have this data property, which is just a tuple of the node ID and this dictionary of extra attributes. So all I'm doing here is I'm just creating a label for each node. I'm just giving it the label 0 if it belongs to this club, which is this is the instructor, and otherwise I'm giving it a label 1. Okay, so I have a tensor of features now, and I have a tensor of labels now, based on the graph that I created. Okay, so in the paper they use this normalized version of a graph Laplacian, and they defined it like that. Okay, and they define this adjacency matrix with a tilde as the regular adjacency matrix plus the identity matrix. And then the degree matrix is just the regular definition, but you're using this tilde version. So it's basically just adding 1 on the diagonal, and you can think about it that really when you're doing that, you're just adding a self loop. You're adding another edge from each node to itself. Okay, so we can see that if you look at this for a second, then you can see that each element in the graph Laplacian is the adjacency between the nodes, and it's normalized by the degree of each node, okay? By degrees of both nodes. So first of all, why add self loops? Can anybody think about that? Why would we want to have self loops in this adjacency term here?
Because every person is more similar to himself, who's close to himself.
What does it mean to be similar to yourself?
I mean, when we have a 0, we don't have self loops. So the absence of an edge probably means that there's no connection between the two nodes. And
okay,
the node to have connection with itself.
Yeah, okay. So a connection of itself, in this case, remember that we use the Laplacian to combine feature maps. We're taking a feature maps and multiplying. So if you don't have this self loop, it kind of means that the output will only depend on your neighbors. If you add this, then you also include your own features to that's the kind of idea. If you look at the definition of the model at each layer L, you're taking the previous feature maps and multiplying it by the Laplacian. So I'm not showing here the powers of the Laplacian or anything. This is just like a more stripped down version. You can just use that as a graph convolutional layer. And if you think about it, what these two parts represent, you have the Laplacian times your features, and you have this weight matrix. Okay, so again, this is not adjacency now; it's weights. So you can think of the first term as combining feature maps locally. So each node is combining features from itself and its neighbors. And the multiplication with this learned filter W is learning how to combine these features to represent the output feature map. Just like in convolutional layers, we want each output feature map to be a function of all the input feature maps. So that's what we're doing here. First, we're using local features, and then we're combining to create the output feature map. Okay, so now let's just calculate based on the definition from the paper. So we have our adjacency matrix. We're just adding this identity for the self loops, creating our degree matrix, and calculating the normalized version of Laplacian, which is the d to the minus 1/2 times a times d to the minus 1 half. Okay? Great. So now we have a Laplacian, we can define our model. So we'll use the spatial version. If you remember, we had two versions of how to define the graph filter. So we'll use the spatial formula, and we'll use the Laplacian from the paper. All we have to do is compute these powers of the Laplacian to locally combine node features. You don't really have to actually use any powers higher than 1. It just, again, it means that you're looking at connectivity that's farther than the neighbors of a single node. Okay, and graphically, what you can imagine here that our model is doing, we have our graph, we have nodes. Each node has multiple features. This is what's represented here by these these rectangles here. It kind of means that each node has C features, and each layer creates new features for each node. Until we get to the output layer, we have these output features. Okay, and in our case, we'll only use labels for two specific nodes, and then we'll backprop to the whole thing to update our learned features, learned weights.
Why is that? Because some labels will be
Well, yes. The problem that we're trying to solve is a semi-supervised classification. So we're trying to use very few labels to classify all the nodes correctly. And in this case, it's kind of an example where we have the graph connectivity given, but we only know for certain that two people will be what their post-split affiliation is. So that's all we know for certain. We'll only use those two labels to train. Okay, so this is our model. This is one graph convolution layer. It's again based on the formula for the spatial version. You can compare this implementation to the formula for the spatial version that we saw before. Let's actually start from the end this time. If you, all this is doing is going over this I have this number k, which represents the powers of the Laplacian. So for each power that I need to calculate, I have the Laplacian to that power. I'm multiplying it by my input features. So x here is a matrix of n by m, where n is the number of nodes and m is the number of features. So I'm creating this Laplacian times my features, which is the extracted features from each node, and then I'm using a fully connected layer, which this represents the multiplication by the W learned parameters. So I'm using a fully connected layer here, and I'm just summing this. Okay, just like in the formula, we're summing over the different powers of the Laplacian times the input feature maps. Okay, and just to construct this, I'm taking the graph Laplacian as an input, and the max deg is this the maximum power of the Laplacian that I want to compute in this layer. Okay, so I'm just for each of these degrees, I'm creating a linear layer, which is just which represents my W, my learned parameters. Okay, and again for each max deg here, I'm calculating the powers of the Laplacian, just saving them. Okay, so that's it. This is really the whole forward pass thing. Of course, we have to add our nonlinearity at the end over the result. Okay, so that's the whole model. That's at least one layer in the model, sorry. So let's create our actual model. So the actual model will have two GCN layers stacked. So we're taking two GCN layers, putting them in a sequential, and adding a log softmax at the end to interpret as probability our scores. So we're defining that we have the number of input features is just the number of nodes in this case. Or remember that we defined X as an identity matrix because we said that each node's features will be one hot vector. Okay, so the first element, the index 1 here in the shape is actually the number of features, but it's also equal to n because it's an identity matrix. And the number of output features is 2 because we want the class scores for each of the two classes. our graph Laplacian, we're just taking the Laplacian that we calculated before, wrapping it in a tensor, and we'll use a max degree of 2 and hidden dimension 10 just because. No good reason. But our layers are defined like so. So we're taking input features. So this is n input features for each node. Then we're transforming it into a graph that has this number of features for each node. So it's 10. And then we have another layer that takes those 10 features per node and transforms them to 2 features per node. So that would be our class probabilities per node. That's how we're going to do the classification. Okay, so that's the model. So training is really just like a classification task with, again, the only nuance here is that we're doing it semi-supervised. We're not using the labels for all the nodes. Just the 2 labels for the instructor and administrator. So this is our training function. First of all, we're using our model over our input features. So this is our input features, which again is an identity matrix, and we're getting an n by 2 tensor here, which is the prediction for each node. Then we're taking our labels. So this is the indexes that we want to use as labels. So this is the index of the admin and the index of the instructor. We're taking our labels in those indexes and our predictions in those indexes and only calculating the loss over that. Okay, so we're not actually calculating, we're not using anything in the y-pred except for the 2 predictions of the 2 specific nodes that we want to use. And again in the labels. So we're basically just ignoring them. I'm just saving it here. I'm saving the whole y-pred for later because I'm going to show you a visualization of what's going on. But I'm only using 2 specific node values from the predictions. Okay, and then the rest is the same. Backprop through the whole thing. Okay, so let's just run it for a second. It's really fast because it's a very small toy problem. And you can see really the loss is going down, but does this actually mean anything? Since remember that our loss is calculated based on 2 samples. So it doesn't mean anything that the loss went down. Maybe we overfit like crazy on those 2 samples. So what we need to do now is take all the nodes and see what the actual accuracy of prediction is for all the nodes. So if we do that, then we will have a really, we'll have what we actually care about. So what I'm doing here, I'm just, after I trained my model, I'm applying it again to the input, getting the final predictions, and this is the final labels, and I'm just using some function to calculate various accuracy metrics here. Now I'm giving it the whole ground truth and the whole predictions. Okay, and sorry? No, I have the ground truth. I just didn't use it. Yeah. Now I am using it to show whether using only 2 labels I was able to predict for the rest that I didn't actually use the ground truth. So now I'm using all the labels, and we actually get a very high accuracy. So we basically, except for 1 node, we managed to predict them all. Okay, so that's nice. But it kind of felt really easy. So after I got that, I just wanted to show you some kind of baseline. So let's compare just with an MLP that does not use the graph structure. Okay, so let's say we have a regular MLP, same architecture. So we're going from input features to the hidden dimension to the output features. Okay. Yeah.
Why do we have 10 hidden dimensions? Like, what's the reasoning behind it?
No reason. You can. It's just so you have some kind of hidden representation that's generated by your model. So you're learning to take the 1-hot vectors for each node. You're learning a bunch of filters that transform the 1-hot vectors to 10 numbers for each node. That's the hidden representation. And then based on the hidden representation, you're classifying. So you're transforming your 10 numbers to 2 numbers, which represent class scores. So that's what's going on here. But here, we're not going to use any graph connectivity. Okay, but the reason is But the question is why would it work? I mean, we just used 2 labels and we backpropped only the loss based on two labels, and we still got high accuracy. So let's see what happens with an MLP. So this is the same architecture, but just using linear layers instead of the graph convolutions that we defined. And we'll train it using the same function now. But much more epochs are required to actually, just to really drive it home. So you can see the loss actually goes down again. Okay, but if we calculate our predictions, then we get a very bad result. If I just run it a few more times, so now it's 0.5. So it's kind of basically a random guess. So even though I trained for many more epochs, and I'm sure I overfit those two specific nodes like crazy, still for the rest of the nodes, it's just no more than a random guess. There's nothing really learned about the rest of the nodes. Okay, so we didn't learn anything with an NLP, but why was the actual graph convolution able to do this, to actually solve this problem when we only trained on those two nodes? Yeah, so what actually happened? We used the Laplacian, we added prior knowledge, yeah, we added the connectivity of the graph. It forced, even if you think about like the embeddings that were generated for the two nodes that we did have, that we did use their labels and we calculated the loss through them, we forced their embedding to be dependent on their neighbors because we used the Laplacian to combine features. Okay, and we even used the degree of 2, so we forced the embeddings to be dependent on the neighbors of the neighbors. So even though we only trained on those two labels, the fact that we put this Laplacian in there, it means that the final embedding that we got for those two nodes was dependent on all of their neighbors and neighbors' neighbors. Okay, so we got a meaningful embedding, and we were able to predict based on that. Okay, so just to wrap up, a quick visualization. So I'm gonna plot the graph, and I'm gonna put the nodes according to their predicted class probability, and color them according to the class that they got. And you can really see like what's happening over the epochs when it's training, how fast it kind of converges. So the axis here, is the probability of each class. So you can see this is the administrator node and the instructor node. They quickly get to 1, and when you train, you're basically splitting this graph into two parts, where you have the nodes that are closer to the administrator, they get higher confidence. The size of the node is the confidence. And as you can see, only one node here is actually misclassified, this 8th member here. Okay, so you can really see like what's going on, how the different class scores are distributed with training, and you can see how this model split the graph nicely, even though we didn't train for a long time, and that's it. So that's it for now. Thanks.